Okay, we now start another section, computability theory. I mean, this is also a very large topic, and it could be, it is in many universities the subject of one course. Unlike Shannon theory, where I used it because the analogy is very, very profound with algorithmic information theory, computability theory is necessary for algorithmic information theory. If we're unfamiliar with what Turing machines are, how they work, how they can encode, how can we encode programs into them, what's a universal Turing machine, and so on, there's no point in doing algorithmic information theory. We lose the whole meaning of it. So my goal here is to establish the basics of computability theory, to motivate algorithmic information theory, and also we're going to be using the tools like the universal Turing machine and so on in algorithmic information theory. So yeah, I would like to maybe dedicate the discourse to a general overview of the theory. I suggested the reading of Turing's paper, which we will see a part of it together. But it's good to get Turing's model right. Many courses in computability theory will tell you this is the model of Turing machines and that's it, take it for granted. I would like to motivate it slightly further via, I think I cannot do better than Turing, so we might reread bits and pieces of section 9 of Turing, because he really conveys the idea of why the Turing machine is the right model to grasp computation. Now, let me start. Algorithms have been around for a long time. For example, the Babylonians.
I think it's a Y.
Thank you. Used some of them, obviously, not all of them. There's plenty of them to discover still. And that was in 2500 BC.
My grandmother once asked me what an algorithm was, and I explained it in terms of a recipe.
Yeah, great.
Recipe.
There you go. I also gave once a public lecture about the uncomputable number of Turing's paper. And I'm like, how do I tell people what's an algorithm? I said, it's a recipe. You follow a list of instructions. It's actually my next sentence, informally. Oh yeah, I wanted to say, well, most of you have coded, I'm almost sure, so you're familiar with what's an algorithm. But even if you haven't, like we've all done some basic arithmetic algorithm in school. You know, we follow a very constrained and fixed and precise set of rules, and we get an output at the end, which is what we want to compute. So informally, they describe a finite procedure I should not say finite, because it might be ambiguous. The description needs to be finite, but the procedure itself may not be. So I'll just leave that out for now. Informally, they describe a procedure that can be performed to compute a desired outcome. Okay, again, when I write that down, I have in mind, I don't know, I'm going to make it up, but 7613, this 17. And have fun, you know, there was an algorithm for that. We needed to divide that number with that number, and it's exactly that. We were taught a procedure that we performed, and we would compute and some outcome. I don't know what the answer is, but we don't mind. Now, in 1936, Church and Turing independently formalized computability theory. And with it, algorithms. So the notion of computing things was around in the 30s. People were discussing it from various approaches. And notably Gödel, that we briefly overviewed, made progress in understanding what is a computation, what is a proof. A proof is a specific kind of computation. And rigor was demanded, you know, in the context of Hilbert, in the context of Hilbert's program was insisting on a lot of rigor with proofs, and then also a lot of rigor in what is the meaning of computation formally. You know, like I could say to my grandmother it's a recipe, but I don't think it will satisfy a mathematician. Now at that stage, we're just going to look into Turing's intro. So I am not going to present Church's take on computability. It is much less intuitive. Turing's take is not only more intuitive as a formal model that we will then see, the Turing machines, but he also explains why it accounts for what we humans can compute. Like via this kind of algorithms with pen and paper and reading and perhaps erasing and so on. So his paper is titled On Computable Numbers with an Application to the Entscheidungsproblem. The Entscheidungsproblem we will leave aside for now. We will really focus on computable numbers and most particularly on the notion of computability. We will come back to numbers. So he mentions that computable numbers may be described briefly as the real numbers whose expression as a decimal are calculable by finite means. He then goes on to say that, yeah, I speak about numbers in that paper, but really the point is not numbers. He could also have spoken about functions or computable predicates, which are a special kind of functions, or other mathematical objects that one can compute. However, he restricts attention to computable numbers. He says, according to my definition, a number is computable if its decimal can be written down by a machine. And what will interest us the most is section 9, in which he gives some arguments with the intention of showing that the computable numbers include all numbers which could naturally be regarded as computable. So he comes up with a model. We will see the model, not via his paper, but via maybe a bit more modern account. And then we will go back to section 9 and we'll go and say, oh, he claims that the computable numbers that crop up in his model include all numbers which could naturally be regarded as computable, in which we can understand like by a human with pen and paper via procedures of these kinds. The big focus of today will be section 9, but I think it's worth to go a bit again in the introduction. In particular, I show that certain large classes of numbers are computable. They include, for instance, the real parts of algebraic numbers. So square root of 2 is not rational, but it's computable. The zeros of Bessel functions, numbers like pi and e. It really encompasses a very, very, very large class of real numbers. The computables number do not, however, include all definable numbers. And an example is given of a definable number which is not computable. This we will not check today, but maybe later. So it's not, one could say, oh, okay, yeah, there's computable numbers, but there might be uncomputable numbers, but we cannot talk about them. One key insights of Turing paper is that he exhibits one number. It's well defined, it's right there, but you cannot compute it. So although that's also an interesting remark, which we will eventually encounter. The class of computable numbers is so great and in many ways similar to the class of real numbers, it is nevertheless enumerable. The word I use in this course is countable. You can enumerate the computable numbers. Conclusions reached are superficially similar to those of Gödel. This is connected with the Entscheidungsproblem, which, if we see, it's going to be a bit later. Yeah, now I should mention that in a recent paper, it was published the same year, Church has also introduced an idea of what he called effective computability, which is equivalent to my computability, but very differently defined. And he includes a proof of this equivalence. So at this stage, I should just maybe just write down here that Turing machines which is Turing's formalisms of computability theory, has the same computing power as the lambda calculus of Church. The set of numbers that can be computed with Turing machines is the same as the set of numbers that can be computed with the lambda calculus of Church. In the 30s, it was sort of a novelty. Nowadays, people come up with very weird ways of thinking of computation, and sometimes they found that it reaches Turing's level of computability, sometimes called Turing completeness. But back in the 30s, we had two a priori different ways of formalizing computation, and Turing showed them to be equivalent. We will come back to that once we check the Church-Turing thesis.
Did those two papers come out the same year?
Yes, they did.
How did this guy, it's amazing that he would, first of all, see the paper and then read it and understand it well enough to determine that it was equivalent to his notion.
I'm also always amazed by that.
Church was Turing's advisor.
Is that true?
Oh.
Yeah.
Okay.
Oh.
I've once said that, but then I've been challenged on it and I couldn't back myself. Always works like that, right? We forget the sources. We just start telling stuff.
Unfortunately, Enigma flew to the US, worked with Church and flew back.
Okay, well that helps if Church was Turing's advisor.
Yeah, okay.
I also think the reason is that in the 30s, it's not like today on archive. Today on archive, there's like thousands of paper. How can you keep up with the literature? But like back then, in that field, I can assume that the number of papers published was readable. Yeah.
By one person.
Actually, if they are equivalent, nowadays the default way, to prove something is using Turing machine. Why nobody use still the lambda calculus?
Some people do apparently. I think that
okay, lambda
For some people that program in Haskell.
in what? In
Haskell is like based on lambda calculus.
yeah. Is Lisp also related to lambda calculus?
Yes,
Yes.
is an implementation of lambda calculus.
Okay.
You have Lisp 1 and Lisp 2, and they are two different semantics, and they build compilers from there.
Okay, thanks.
But also, I think this also supports loops and stuff.
Of course.
Yeah.
But also Haskell supports.
No.
Of course.
No, only the version.
Try to Google it. Haskell for loop. Yeah. There is an abstraction, of course. It's not like a C for loop, but there is loop. You can do loop also in Lisp. Yeah. implementato dentro? Non lo so.
Okay, Turing's model of computation.
Usare do. E anche for loop è una porcata.
He exhibited a simple type of machine actually it's a type of, I should say, hypothetical machine. And argued that everything that can be reasonably said to be computed by a human computer using a fixed procedure can be computed by such a machine. So everything that can be reasonably said to be computed by a human computer using a fixed procedure can be computed by such a machine. That is section 9 of this paper, to which we will come back, but at least I wrote the generic idea once, and then we will see his argument once we revisit section 9. But for now, let's go. What's a Turing machine? What's the model? So, a Turing machine is or consists of, there are a few things. One of them is an infinite tape of cells. Which contains either a 0, a 1, or capital B for a blank. The beauty of Turing's construction is that I sort of define the things just by referring to your imagination. An infinite tape. Oh yeah, tape. It's broken down into cells. Obviously, I also know that most of you might have already seen Turing machines. Blank is an extra symbol which represents nothing. There's nothing written on the tape. Well, actually, I don't even like to think of it as a symbol, but it's a blank, whatever that is. So, okay, yeah, let us have a construction here. What have we got? We've got an infinite in both directions. Infinite tape. It's broken into cells. And on the cells, there are going to be either blanks, like here is a blank, here's a blank, here's a blank. Then maybe a 0, a 1, a blank, a 1, a 0, a 0, a blank, a 1, a 1, a 1, a 1, and then blanks, for example. That's my tape. It also contains a head. This is not to be mistaken as like the mathematician's head. It's more like, or a pointer, some people say. But I will use a head. And the idea is that this head is capable of scanning a cell. So let me draw a head, just as, for example, this. My head is an arrow, and at that moment it is scanning this cell on which it is written 0. It also contains a finite control. Which can be in any one of a finite. Oh, that will be annoying already. Okay, I'll write here. Of a finite set of strings. No, set of states. And the set of states is denoted capital Q. Okay, and just for, as an example, Q will contain stuff like Q0, Q, Q prime. This is the kind of thing I'll be using to denote specific states. If I can, I'll use lowercase q to design one specific element in the set, capital Q. Yeah, so the finite control, you can think of it as, this is where the processing is happening. It has, possible states, like Q0, I said Q prime, perhaps some other. And there is one state in which the Turing machine is. So, which can be in any one of a finite set of states. So, I'm also going to denote it with an arrow. For example, at that instant, my Turing machine would be, yes, reading that symbol, but that's another thing. It would be in the state Q. And I also add that the finite control contains, yes, a finite set of states, but and embodies a list of rules. And this is your grandmother's recipe. It's the list of rules. So I'll just represent it here as really a list of rules. We'll see what they consist of later on. But they basically encode what the Turing machine needs to do now that it is in state Q and it's reading a symbol 0. It needs to do something. It's going to check in the list, and the list will tell it what to do. It's going to be extremely precise, unambiguous, formal, no place for error. So yeah, this was the continuation of that point, of A finite, and then I add an extra point. I like to think that in the background they are discrete times. Zero, 1, 2, and so on. I'll put a... Oh yeah, this is my finite control. This is my list of rules, it's written. This is my head. It's not mine, but it's the Turing machine's. Okay, any questions for now? Out of curiosity, who has already seen Turing machines but in a course, not by curiosity? Okay. Who has not seen Turing machines in a course? Okay. Who has read about Turing machines by curiosity? Who has not? Okay, good. Even if all of you would have said, yes, I've seen a course on it, I think it's at least a valuable reminder, but that's just out of curiosity. Guess I get to know you more. Discrete times, okay. Okay, that I won't write it down, I'll just do a drawing. A computation starts at time 0. This could be the initial time. The time at which the computation starts. And I'll draw another Turing machine that is in its initial configuration. So at the start of a computation. Yeah, I guess it's going to be more fun to draw a picture than to write it down. So it starts in a given initial state, which is known, which is specific. It's going to be Q0 for our purposes. This is the initial state. If you will, initial distinguished state. You also have the other states, but right now it's in Q0. It's going to be my initial distinguished state. It also has, well, it still has its infinite tape, of course, that doesn't change. But what it also has, which was not made explicit here, is that there's a distinguished cell.
Starting cell?
Correct, yes. Let's say it's this one. It's a distinguished, let's call it the starting cell. And the starting cell is blank. All the cells to the left of it are also blank. But there will be a bunch of non-blank cells to the right of the starting cells. I'm going to write them as an example. 0, 1, 0, no, 1, 0, 0, 0, 1, 1, 1. And suppose I stop here so that you understand the vibe. Yeah, this binary string here is called the input of the Turing machine. I'm going to rewrite it again in green just to make it clear. Okay, so the input is defined as the contiguous finite string which initiates just on the right of the starting cell. And all other cells of my tape, of the tape, is blank.
Can the input have blanks?
Pardon me? Yeah, the input can be blank.
Can it have blanks inside? Between like zeros and ones?
Good question. No. Input is only zeros and ones. You will quickly realize that there's many ways of defining Turing machines. The reason why I taught is not because it really matters. It's because I want to be consistent with my notes so that this is the model I express and we will move forward with that model. But some people have come up with Turing machines with 2 tapes, and we will at some point, I think. It can be convenient to have an input tape on which you cannot write, for example, and a work tape on which you can write. We will at some point do that. And you can also, some authors say that the tape is semi-infinite. So it doesn't go to infinity on the left, it just goes to infinity on the right. But then there's a huge bunch of results which say that, oh well, they can all simulate one another. So who cares? Let's fix a specific model. Now, with regards to your question, the input, I demand that it's only with 1 and zeros. Zeros and ones. Okay. Questions so far? We'll continue with the operations that it can make. So the time steps will become relevant for the operations because the Turing machine performs one operation per time step. In which it either there's 2 things it can do. So this was my initial Turing machine, that's its initial state. We can look at what it does in this initial state, but why not here? It's a generic configuration of my Turing machine. It's in my example here, the Turing machine is in state Q. It reads 0 with its head. It's going to go in its list of instruction, and the instruction would tell it what to do. One of the things it can do is to forget that 0 and write something else. Well, something else. It could be a 0, which wouldn't be something else. It could be a 1, or it could be a blank. He can write a blank if he wants. I now personalize the Turing machine. It's now a person. I said he, but let's say it again. Yeah, so one of the things it can write either no. I want to be more concise. It writes 0, 1, or B in the scan cell. That's one thing it can do. Or it can also move the head left or right. And it does either that or that, depending, as I said but I didn't write, on the current instant Q, the current state, and the scan the symbol. I was about to say it's a person again. The Turing machine is not exactly done. This is what can be done on the head, but after having done something here, like either moving left, moving right, writing some other symbol here, it can or cannot change its state. At the end of each step, the control takes a possibly different state. I will put possibly different in parentheses. Let me call it Q prime in Q. For a given Turing machine, its set of operations is given by the finite list of rules. Each of the form Q, S, A, and Q prime. So there's a list of rules. One rule will have the form of a quadruple, Q, S, A, and Q prime. I'll tell you what each of them are, so you understand the logic of the rules. Yeah, this Q is the before state. I didn't want to say initial state because we've already used the word initial state for the state at time zero. But it's about to perform a rule. In our example, it was in state Q. So it's before doing the operation. It was in that state. S stands for the scan the symbol. So right away we have that Q is in Q, S is in 0, 1, or blank, because it's the scan symbol. A is a little more tricky. Okay, so this tells you, this is basically, if you are in that state and you read that symbol, then do that and that. A stands for action, if you want, which is going to be an element of, I said it can take two kinds of action. It either writes a 0, writes a 1, writes a B. That's the first kind of action. And the second kind of action is that it moves its head. But all of those two actions can be encompassed by this. 0, 1, B, L, R. If the action is 0, it means you write a 0. 1, you write a 1. B, you write a blank. L, you move the head to the left. R, you move the head to the right. And Q prime is going to be the after state. Also in Q. So yeah, maybe I could add, we have a bit of an idea. The list of rules will look like a bunch of quadruples. Q0, 1, and then do right, and go into state Q prime. That would be one rule. Or if you have Q0 and you read a 0, then write a 1 and go to state Q. Whatever. There's a list of rules like that. Oh, and yeah, I've already been pushing it a bit. I won't be pushing it more. Let's have a break and reconvene at 35 past. Okay, I'll start again. So where were we? We saw that, okay, I explained how we can encode the list of rules via quadruples. The two of them being the, if you want, the initial or the before configuration. Configuration is a word often used with Turing machines, and it means both the state of the finite control together with the information of the symbol that is being scanned by the head. So the initial configuration or the before configuration and the after configuration, which is, it embodies the action, what it does. Does it write a 0 or 1 or blank? Does it move left? Does it move right? And what's going to be its final state or its after state, I wrote, just after the step. The step is really like a very elementary thing that can be done and which cannot really be broken again. How would you break it? Now, what I like to say is that, I mean, we can define various kinds of Turing machines, but we will be interested in deterministic machines. So the machine is deterministic. Which means that Q S A1 Q prime 1, and so that's a rule. It tells you what to do if you are in configuration QS, and another one which also tells you what to do if you're in configuration QS. But it tells you something different. Imagine it tells you do action A2 instead, and go into state Q prime 2. So these two cannot both be rules. Of the list. If it's only meaningful if obviously if the tuple A1 Q1 prime is different than A2 Q2 prime. In short, these two rules together with a different A1 Q1 prime than A2 Q2 prime will not happen. Because if you have that, you have a non-deterministic machine. You get into a state Q and you read symbol S, and then one rule tells you, okay, move to the right and go into state number 17. But then another rule tells you, no, right is 0 and go into state number 130. The machine would not know what to do. There would be two possible rules. It would not be deterministic. Deterministic means that given a configuration QS, there's a unique thing you gotta do.
So A is a function.
Yes, I finished with that, yeah.
Okay.
It's actually very convenient to write them as tuple, quadruples, but at the end of the day, it's a function of this onto this. Correct. Okay, and there's another constraint. Moreover, well, it's not a constraint. In fact, the other one is more liberal. Moreover, not every possible combination of the first two elements has to be in the list. The first two elements being here Q and S. You might reach a state Q and you're reading a symbol S, for which you look into your list and you go like, there's no rule. I don't know what to do. That's fine. What the machine does in that case, it halts. Because it has nothing to do. It says, all right, I'm done. Halt. Yeah, I did a column in my notes. So column. The machine might perform no operation in which case as Giacomo observed, hence, the transition of a Turing machine can be defined by a mapping from I'll say a subset of what are these guys can be in? Q is going to be in capital Q. S is just the scanned symbol, so it's only 0, 1, or blank. So a mapping of Q times 0, 1, and blank onto we can really understand it as the idea of a mapping is that it has an input-output relationship and it has a single output. And a single output is guaranteed by that constraint here, the deterministic property of the Turing machine. But this A is an action. So this A belongs to 0, 1, B, L, R cross a state, Q prime, which is an element of capital Q. Yeah, so the deterministic constraint is embodied by the fact that it's a mapping only for each element here that is in the domain. A single corresponding element here will be defined. That guarantees a deterministic property. But then the fact that not every possible combination of the first two elements has to be in the list is given by this constraint here, that the mapping is a subset of this part here. So it's not defined on all elements of that. In general, it might be for some Turing machine, maybe it's defined for all pairs here, but in some cases it might not be. Again, I repeat the idea. I have a list of instructions, and what this says here is that you might eventually get into a configuration Q, a state Q reading a symbol S, for which in your list there's no instructions. It doesn't tell you what to do. Then you halt. That's what this said. And when you understand the Turing machine transitions via this mapping, it simply says that, well, the Q and the S that you found was not in the domain of definition, because your domain was just a subset of that. Okay. A given Turing machine, we finally get to computing a number or computing something. A given Turing machine on a given input carries out a uniquely determined succession of operations which may or may not terminate in a finite number of steps. That's an important feature, and I have not attracted your attention to that yet. So, yeah, because the machine is deterministic, there's an input just next to its initial scanning symbol, initially scanned symbol, and eventually it will it starts in that configuration, and it will apply the first rule. It's in initial state Q0. It's going to check into its list. It says Q0, you scan a blank, you've got to do something. And there's a list of those rules, and it will be doing those rules deterministically. One operation per time step. You right away realize that you can make it loop. You can say, move to the right, move to the left, move to the right, move to the left, move to the... And it's just going to get stuck into a cycle like that, alternating infinitely between states. So what I write down here is that a given Turing machine on a given input carries out a uniquely determined succession of operations, which may or may not terminate in a finite number of steps. Yeah, some Turing machines on some inputs will never halt. Again, the condition for halting is that the Turing machine reaches a configuration, so a state together with a scan symbol in which there's no rule. This we take it that it's a halting state. We're not done. When it halts, we say that it has computed the string on its state. After halting. And that string is called the output. Yeah, so it starts like that. This is a fixed Turing machine. It has a set of rules, a set of states, and then it's going to do something, a bunch of operations. If that Turing machine on that input halts, well, most likely what's going to be written here is going to be different. It's going to be some strings. Remark that if it halts, there's infinitely many blanks in that direction at some point. It cannot have put zeros and ones infinitely far. Unless it doesn't halt, it could do that.
And also in that direction?
And also in that direction, yeah. So it's a well-defined string that's left. You could say it's start with the first non-blank symbol, and that will be my first symbol of the output string. Now the output string also may contain blanks. Now it's a matter of taste. Do you keep the blanks or do you remove the blanks? I don't think I made a choice yet, and I don't need to. When we get to algorithmic complexity, we will want that the outputs are just zeros and ones. So I guess we'll remove the blanks. Good. So that's the Turing machines. That's how it works. There's plenty of Turing machines, right? There's as many Turing machines as I can think of, finite number of states, which entails rules. There's many of them. In the introduction of Turing paper, it was said, though, that they're countable. You will see that fairly soon. I guess not today, but I'm pretty sure you can think about it right away. It is, what defines a Turing machine is going to be something that can be put into correspondence with the natural numbers. So that's why he said that there's only countably many computable numbers. Now, I guess this is probably the most non-technical part of the whole course, but we're going to go into section 9 of Turing paper. out of curiosity, and there's absolutely no judgment, but who has read it? Okay, parts of it. It's worth reading it for those who have not read it, but it's really worth rereading it if you have already read it, because you might see some arguments that you, I guess, didn't appreciate in the first reading. I reread it, like, when was it? 2 weeks ago, 3 weeks ago, when I was in a conference with a bunch of computer scientists, and they said, "Oh, you're reading Turing? Why do you read Turing?" And I'm like, "Section 9 is so nice." And I think that in many theoretic computer science book, the point of section 9 is omitted, because a theoretic computer science book will do what I've done here. It will tell you what's a Turing machine, and then we go on with the theory, the existence of universal Turing machine and whatever other theorems we're going to prove, but it doesn't justify why the Turing machine is relevant like Turing did in his section 9. It's long papers. There you go. Section 9. Do you see well? Mm-hmm. Okay. It's titled The Extent of the Computable Numbers. Yes. In the back of your mind, I asked this question. According to you, is that mathematics or is that physics? I asked the question now, but don't answer it yet. But have it in the back of your mind. Yes, I guess the easy answer is no, it's computer science. It's like a seminal paper in computer science. But in 36, I don't exactly know if there was such a thing as computer science. It sort of sets the basics of computer science. So should it be understood as a piece of mathematics, or should it be understood as a piece of physics? He says, no attempt has yet been made to show that the, quote, computable numbers, by which it means the numbers that can be computed with Turing machines. Oh, I haven't told you what that is. In fact, yeah, I guess I'm not exactly sure this is what Turing used as a definition, but a number is computable if you give it as an input a string which represents a number n. I assume now you're all aware that with strings we can understand them as numbers. It will do a computation and it will output the n first bits of that number. Okay, so if we want to compute pi, I know you know algorithms to compute pi, like pi is, for example, 4 times 1 minus a third plus a fifth minus a seventh plus da da da. It's a very slowly converging series. You could do much better with other series or other ways of thinking of pi. And then you can program that. And you have as input n, and you're asked to produce pi n, the first n bits of pi, as an output. And if there exists such an algorithm, which is fixed, because n is an input in this case. So for all n, it will produce the n first bits of pi. Then we say that pi is computable. And just by the fact that I wrote it down like this, I'm sort of giving you an algorithm. It's implicit, but you can imagine that you could program a computer. Now I'm cheating. I'm not really programming Turing machines. I don't know who would really program Turing machines. We will see that Turing machines are as powerful as naive algorithms. So we will always be thinking in terms of naive algorithms. You guys have worked with real computers, so I know you know not only naive algorithms, you know Python or whatever programming language you know. So from that, you can make an algorithm which will eat n as an input and which will spit as an output the first n bits of pi. The same holds for e, or for square root of 2, or for many, many, many real numbers which are not necessarily fractions, because they have a way to grasp them by a finite recipe, like the zeros of the Bessel functions, or most of the numbers we work with are in fact computable, even though they might be irrational. So okay, that is the context of computable numbers. And in quotes here he says computable, but now we understand it, computable by Turing machines. No attempt has yet been made to show that the computable numbers include all numbers which would naturally be regarded as computable. There's two senses of the word computable. One with square quotes, which means there's a Turing machine that does that. It computes the first n bits of that number given n. That's a formal definition. And in section 9, what he wants to do is that it encompasses what one would naturally regard as a number being computable. Again, have in mind, is that a math paper or a physics paper? All arguments which can be given are bound to be fundamentally appeals to intuition, and for this reason rather unsatisfactory mathematically. The real question at issue is, what are the possible processes which can be carried out in computing a number? The arguments which I will use are of three kinds. A direct appeal to intuition. This is the one we're going to see. And he also gives a proof of equivalence of two definitions. I mentioned that he proved it equivalent to Church's lambda calculus. So we're not going to see that proof. And he's giving examples of large classes of numbers which are computable. I also gave you some, but he's giving them also. That he basically says how you can program a Turing machine for pi. And I think this is his recipe too. Because he appeals again to intuition with the fact that since you have this form of procedure, you could, in principle, step-by-step program a bunch of rules which would halt with pi n on input n. Yeah, for us what's going to be more interesting is the appeal to intuition.
But how do you know when to stop?
Oh.
Like if you want to use that series.
Oh yeah. You need to know some analysis of convergence.
Oh, yeah.
So for example, here, since it's an alternating series, you know that the error would be at most the last term.
Okay. Yeah.
If you want to stabilize n bits in the binary expansion, you need that number to be smaller than 2 to the n.
Yeah.
It's a good point. Sometimes it might not be clear when to this analysis. It needs to be a part of the algorithm. I said smaller than 2 to the n. I think I meant 2 to the minus n. So, okay, here he goes. What he does is he wants to argue that this model here is what a mathematician with pen and paper would consider computable. I just love that. How beautiful is this? Computing is normally done by writing certain symbols on paper. We may suppose that this paper is divided into squares, like childhood arithmetic book. In elementary arithmetic, the two-dimensional character of the paper is sometimes used, but such a use is always avoidable, and I think that it will be agreed that the two-dimensional character of paper is no essential for computation. Right? So he takes a paper, he divides it into grid. He says, yeah, it's two-dimensional, but really you can do without it. You could just have a long strip of paper. What is he building now?
The tape.
The tape. I assume that the computation is carried out on a one-dimensional paper, i.e. on a tape, divided into squares. I shall also suppose that the number of symbols which may be printed is finite. That's an important assumption. So he says that what you can write down on each square is a finite number of symbols. He justifies it. If we were to allow an infinity of symbols, then there would be symbols differing to an arbitrarily small extent. And in a footnote, I'm not going to read the footnote, I'm going to explain it to you. It's just how brilliant it is. He says that the square is finite, and you can define a metric on the space of symbols. You know, like two symbols will differ by a lot or by a little bit. If you can sort of, the amount of ink that you need to move, I think that's what he used. But you can define a metric. And since it's finite, it's a compact. And so you would have, if you have infinitely many points in a compact, you will get an accumulation point. That's an analysis argument. So two symbols will be arbitrarily close to one another. and so undistinguishable with human eye. There you go. You have an argument that for all mathematical pen and paper computation, we might as well take the alphabet finite, otherwise you'd be confused. He says, but despite saying that, he also mentions the effect of this restriction of the number of symbols is not very serious. It is always possible to use sequences of symbols in the place of single symbols. And he gives example with, a numeric numeral such as 17 or that large number is normally treated as single symbol. Similarly, in European languages, words are treated as single symbols.
We were just talking about this.
The Chinese?
Yeah, we literally at lunch we were talking about that.
Yeah. He mentions that Chinese, however, attempts to have an innumerable infinity of symbols. Interesting. The differences from our point of view between the single and the compound symbols is that compound symbols, if they are too lengthy, cannot be observed at one glance. This is in accordance with experience. We cannot tell at glance whether that number here and that number here are the same. So basically, he says if you might want to have more symbols, you're just going to use more squares. But then you're going to have a similar problem, which is going to be, they might be hard to distinguish at one glance. So you might need like a procedure to, for example, you could count the number of nines. That's what I would do if I would have to distinguish between this number here and that number here. And eventually I would, make a sub-algorithm which tells me, oh yeah, they're different or they're the same. Okay. He goes on to say the behavior of the computer at any moment is determined by the symbols which he is observing and his state of mind at that moment. That should ring a bell. The behavior is determined by the symbol that is observed and the state of mind. The state of mind is what we call the internal states, the cues. Now my question for you is, what does he mean by computer? They were not invented.
Person, a guy with pen and paper.
Yes. It's like almost like a beautiful joke. In Turing paper, yes. Exactly. It's a person with a pen and a paper. But like for us, modern child of the 2000s, we read that and we're like, did he already have computer? It might be confusing. No, he was referring to people computing things. They were called computers. But we read this and it almost works as like a physical computer now that we have them. Yeah, so the states of mind are the states in which a computer as a person could have his mind. Like, oh yeah, I just read the symbol of an integral, so I'm about to do, in my state of mind, I will have some algorithmic functionalities. We may suppose that there is a bound B on the number of symbol squares which the computer can observe at one moment. I'm sure that your eyes cannot see infinitely many symbols at one moment. This bound, in my case, it's like 5. I'm really bad to read fast. If he wishes to observe more, he must use successive observations. We will also suppose that the number of states of mind which need to be taken into account is finite. So now he's arguing that not only the alphabet of symbols is finite, which we took binary, but that the set of cues is also finite. The reasons for this are of the same character as those which restrict this number of symbols. If we admit an infinity of states of mind, some of them will be arbitrarily closed and will be confused. I like the word confused. It makes me think that the person just gets confused because he's got to distinguish between two states of mind which are very, very close to one another. And then he goes on to say again, the restriction is not one which seriously affects computations, since the use of more complicated states of mind can be avoided by writing more symbols on the tape. That's something we do. Like if we're about to do very complicated calculations, at some point we might not just keep everything in our mind. We're probably just going to take an extra piece of paper, write down some notes to help us with our computation. Okay, I keep going a little bit because I think it's too nice. Let us imagine the operations performed by the computer to be split up into simple operations, which are so elementary that it is not easy to imagine them further divided. That's what we did. Each such operation consists of some change of the physical system consisting of the computer and its state. We know that the state of the system, we know this state of the system if we know the sequence of symbol on the tape of which these are observed by the computer, possibly with a special order, and the state of mind of the computer. We may suppose that in a simple operation, not more than one symbol is altered. So he has a scanning head in which he can alter only one symbol. Now, you have remarked that he gives the observation of the computer a wider range than we did. He said, like, you can observe B symbols at the time, whereas I just said that the transition function is only a function of the symbol that is scanned. Now, it can be shown that you lose no generality by shrinking B to just one. You have to make this more complicated, but it can be done. Okay, what's next? Beside these changes of symbols, the simple operation must include changes of the distribution of the observed squares. Yeah, this is also something we did. Not only we want to change the written symbol, but we want to look at other squares. He also mentions that the new observed squares must be immediately recognizable by the computer. I think this is reasonable to suppose that they can only be squares whose distance from the closest of the immediately previous observed squares do not exceed a certain fixed amount. He calls this amount L. So he also introduces an extra parameter that we don't have, which basically says that you can, after you've read that one, you can move, but only as far as L symbols. Right? It also corresponds to what we do. When I actually carry down a computation with pen and paper, after a step of computation, I'm not jumping arbitrarily far. I can only look at what's next. Now again, we reduce that L to 1, but it can be shown that no generality is lost by doing so. Yes. Okay, I just skip a little bit. And yeah, he basically wrote what we wrote. The more general single operation must therefore be taken to be one of the following. A, possible change of symbol together with a possible change of state of mind. And B, possible change of observed square together with a possible change of state of mind. Now, I guess I will stop here because I want to keep a few minutes to discuss. So is that physics or math?
For me, it's called mathematics, but probably it's because I studied mathematics in my bachelor. So it just sounds familiar.
Yeah. I have to grant, he uses math. It's mathematical. He formalizes this with sets and stuff. But so do physicists do when they write paper. They formalize physical systems with mathematical structures.
But they just use math.
Sorry?
They just use math.
They just use math?
Like they don't study math as math. They just use math as a tool.
Yes, exactly.
So it's different.
Well,
I don't know, because yes, he built a physical system, but I don't know if he built only to explain, for example, because I think that if this is physics, also lambda calculus should be physics, and this is, I think, is difficult.
Why?
If they are equivalent.
Sorry?
If they are equivalent. Or if they are the same thing.
Calculus?
Lambda calculus, yeah.
Oh, lambda calculus.
Yeah.
Yes. Okay. I thought just differential calculus. For me, it was a leap. Okay. Yeah. Well, okay, general relativity is four-dimensional manifolds with curvature. It's very mathematical. You do covariant derivatives and you solve Einstein's equation. You can write them down as tensors. It's highly, highly mathematical. My claim, and I know it's I would say I might be attacked for proposing this claim, but is that what Turing did, I'm not even sure he was aware of that, is that he really did physics, but with a special kind of physical system, namely a mathematician. He tried to formalize mathematically what this physical system is, namely the mathematician with a pen and a paper. And this is where he goes on to, I have intuitions and I give arguments. There's no proof. It's a conjectured toy model of how this thing works. The thing I'm pointing is a mathematician. Oh yeah, it works with a finite set of states, which I could formalize and set theory with those objects. It has a tape, which, by the way, I haven't even formalized it. I just wrote a tape, and I appealed to your intuition of what is a tape.
I mean, but like you didn't actually formalize something that is the same as a mathematician, because like, for example, if you take like some proof of some random theorem, you cannot do it on a Turing machine, while a mathematician technically can do it.
Why not?
Turing, because like proof of a theorem is not, it's like not, how to say it, it's not a problem that Turing machine can work out. Theory, which is the algorithm to prove a theorem.
We will address that. So I mentioned in the first course that we will revisit incompleteness in a more satisfactory way. We will revisit that. So
there is no algorithm that I know to use it. Like okay, otherwise like when you do.
There is more than that. There is an algorithm which spits all the theorems of a given formal axiomatic systems.
Yeah, I mean, a proof of a theorem is already an algorithm. Like,
yeah, that's an algorithm, but the algorithm that creates the algorithm of the proof.
You can do infinite steps, I think. You can you build another Turing machine that define the Turing machine that prove things, and I think there is a way that show you that you can build it in a fixed number of steps, I think.
So you're saying like that you create a Turing machine,
yeah,
that creates another Turing machine.
Yeah.
But then, like, how can you say that that Turing machine is correct if you cannot even say that that Turing machine alt? Because the alting problem is definitely not Turing computer.
Mm-hmm.
So, like, you cannot.
But for theorems, if you have a formal theory, maybe I should not say it now. I want to tell it to you, but I don't want to be stealing my punches from my. I think in 3 or 4 courses we're going to precisely discuss that. But if you're too curious, come and see me. But yeah, the notion of Hilbert's program to be, to have a set of axioms which is highly, highly rigorous and formal, we right away see that it goes a bit hand in hand with the rigor that we use for Turing machines. Now, this is no argument that a Turing machine can know the axioms of set theory or of geometry or of whatever. But if you give it rigorous axioms, well, then we can build from those rigorous axioms and inference rules programs which will generate some theorems. Like, it could generate the axioms. The axioms are a theorem.
Yeah, okay.
It can generate just one more level. Take a first axiom and apply one rule of inference, and it gives another theorem. And then it can start to search into the space of all possible things it could do in the symbolic language and spit out theorems.
Yeah, but you cannot prove it. Otherwise, for example, you can prove that P is equal to NP or disprove it by just writing a program. Why, like, people are saying, like, why it's the same if you can write a program that does it for you?
We will have fun.
No, but I think
really?
Because the point is not of, for example, P versus NP. Okay. The point is that maybe it's possible to build an algorithm that can solve all of them in polynomial time. But the point is that we don't know.
Yeah, that's all okay.
Nobody ever never written this program. Maybe it's possible because there is no proof that say that okay, you cannot do it. So or you prove that it's impossible, or you provide an algorithm that prove that solve one instance of the problem.
Yeah, but that's what I'm saying is a bit different. What I'm
Okay.
saying is like if you have a Turing machine, you state that like Turing machine can prove a theorem, a random theorem
Not from nothing.
from nothing. Like I mean, okay, you give the axioms.
Okay, that's the
You have the axioms, and like just from the axioms, it's like not that there is some hard-coded proof, but gives you the algorithm to prove that theorem from scratch.
Yeah, I think that
It
you
can.
use writing rules and it can be done.
It can.
We also do that, but we don't know whether we will halt or
Yeah,
not
exactly.
sometime in the future.
But you can't say that. You know,
You have you give all the axiom and all the list of rewriting rules that you can apply, and you say, okay, choose one rule and try to apply again another one.
okay, and you explore all of them.
Yeah.
Okay.
But yeah, because
it's
the
true.
space.
If P really equals NP and it's a logical conclusion, say, of the...
Why no one did it? This point.
Why? Tell me.
Maybe the proof is very long.
Yeah, it's
And your Turing machine
computational
will need to
time.
run for a long time before it stumbles upon the one random, very, very long proof that shows.
Ironically enough, you fall into P versus NP.
Yeah.
Implicitly.
Yeah.
Because by doing an exhaustive search, if there's a proof, you will eventually find it, but if P is different than NP, that algorithm might be exponentially
Yeah,
long.
but the Turing machine then how does it say that like that proof is correct, for example?
Well, that is given by the rules of inference and the symbolic system. You can just say there are actually proof checkers that exist. There are algorithms out there that you input the proof and you ask, is it correct? And it's going to check symbol by symbol A if it's syntactically correct, and then B if it's a logical conclusion from the axioms. It's going to verify.
Okay.
It's going to verify the steps. The actions the questions you're asking are really good. I please do not repress them, voice them. They're really, really good. I feel like I have to retain myself because otherwise I'll be stealing all my punches.
But you don't fall into the P versus NP in this case, right? Because your input is just like a constant length. So your algorithm does not vary as a function of the input. So
It's a good point. I think that the parameter comes into the length of the statement.
Right.
Yeah, but I just feel that it's easy to check, but difficult to generate.
Exactly. So this is where and what the mathematician does is precisely not exhaustive search through all theorems. He tries to come up with intuitions, arguments, whatever, but he's definitely not brute forcing the system. That's for sure. But we put our finger onto something that will be useful later on to explore the limitations of formal axiomatic systems. And now I have less hand-wavy tools to speak of what's a formal axiomatic system than I had on day one. Because I could say that a formal axiomatic system needs to be recognizable, say, by a Turing machine. We will define all of those in due time. But a Turing machine can, say, understand it, at least the syntax, and manipulate the axioms with the rules of inference and start to do quote-unquote non-trivial claims.
As to is it mathematics or physics, I think he probably meant it in the spirit closer to mathematics, but it is similar to physics in the sense that it feels to me like he's attempting like the first reduction ever. He's trying to reduce a human, like a mathematician with pen and paper, to his Turing machines. And there's a lot of hand-waving in there, but assuming it's true, then he's sort of implicitly describing a physical system, because a human is a thing with a brain and electrons and protons and whatever.
Yes. If he is right in his attempt to formalize a mathematician together with a pen and a paper and a pair of eyes and a brain, if he is correct that this is a correct formalization, then the limits of this formalism will also be limits of us, of what we can or cannot prove. And he exhibited an uncomputable number, so there's a number he can define for which no Turing machine.
Oh, can we see that? Is that in the paper?
Yes,
Is that gonna take
I'm
very
really
long?
pushing it by the way, and I don't want to be retaining anyone. The course is over, feel free to go. But I don't think there's anyone after us. That was at the beginning, right?